Might be in. I'll take it. All right.
You want it?
Yeah.
Good in Florida?
Are you in a better mood?
I'm always in a good mood.
Scared you for a little bit.
So we will begin on Friday. We were talking about artificial neural networks. Towards the end, we discussed a little bit about at least some of the big ideas involved in deep neural networks, so you got to see a little bit of that. Are there questions about anything we discussed on Friday involving neural networks, or anything about classification up to this point? In Florida? Questions? You're good? So today we're going to discuss, I mean, there are a whole bunch of other ideas even within classification that we're not even going to cover. There's many different algorithms. Today's main topic is what are called ensemble methods, or another term that you might hear is model combination. And again, I'm only going to be looking at kind of a subset of many different ways of combining models. Data mining, part of it is you have many different people going in many different directions, discovering and inventing many different ways of doing things, and in this particular example, coming up with ideas on how to classify, to get machines to classify for us. So with that introduction, we'll bring up ensembles.
Where's its origin?
Well, it depends upon the methods that we're going to be looking at. So you mean the origins of ensembles in general? I don't have an answer to that. I could find it for you. But I have answers for some of the particular methods that we're going to be looking at. So, ensemble methods, what are they? And why do we use these? So we've already discussed a number of different basic classification algorithms. We started with decision trees. We moved on to rule-based classifiers, and I can't remember what we did next. Did we do support vector machines right after that? Artificial neural networks. And ensembles, sometimes the best algorithms we have, well, we talked about Bayesian classifiers as well. Sometimes we have classifiers that by themselves are okay, but still somewhat weak. So ensemble methods are a large class of methods that will take other methods and combine them. So you're going to create different models, or maybe multiple models of the same type, depending on the particular ensemble method that we're going to look at. And so combine these multiple models to obtain a model better than any of your individual models. That's the basic, simple concept behind ensemble methods. Is that part fairly clear, James? So if you take a look at the subtopics here, we're going to construct from a training set, we'll construct multiple classifiers, and then we're going to aggregate their predictions on a testing set. There's more than one way to do this, so we're going to go into some of the more basic ones. You can think of ensemble methods as a meta-algorithm. So it's an algorithm for combining other algorithms. And we'll even possibly talk about meta-algorithms. So the point of ensemble methods is, in general, we're going to use ensemble methods to improve stability of our basic methods. Stability, accuracy, predictive capabilities. Ensemble methods typically will reduce the variance that we have with a particular classifier. So by combining if you think statistically, if you obtain an average, you tend to minimize that variance compared to individual outcomes. So if you look at averages of heights, they tend to vary less than individual heights. And so the same kind of principle applies to ensemble methods. Ensemble methods we can use to help avoid overfitting. And in general, so I alluded to this on the prior slide, compensate for poor learning algorithms. So even if your algorithm is not that strong to begin with, we can make it strong through some sort of averaging or other ensemble methods. Averaging is one, but there are many other ideas there. The downside, the price for obtaining better accuracy, better predictive capabilities, less variance, and so on, is it's going to require more computation. No free lunch, so to speak.
I like free lunch.
There's a theorem called the no free lunch theorem in mathematics. So, some basic methods that we'll talk about. Really big one is called bagging, which is short for bootstrap aggregation. A subclass of that's using a particular weighting kind of algorithm called metacost. We'll discuss that. A relative of bagging, it's kind of like bagging on decision trees, or tree learning in general is called random forests. So some phrases you should be familiar with. A whole other class of algorithms is called boosting, of which the most prominent is called AdaBoost, ADA, short for adaptive boosting. One that I've used quite a bit in my own work is called stacked generalization. One of the big advantages of stacked generalization, or stacking, is that you can, unlike some of the other ones, bagging and boosting need to be applied to the same type of algorithm. So if you have you have a suite of decision forests or rule-based classifiers. Stack generalization works well with in terms of combining different types of algorithms, different classes of algorithms. And the last one that we'll talk about, although there are others, there's bucket of models. There are many others in the literature. We're going to pretty much stick to these 5 basic types. The last one being Bayesian, there's the Thomas, I think it's Thomas Bayes again, Bayesian model combination. So bagging. So I mentioned we've already encountered the term bootstrapping.
Bootstrap build.
Okay, and that's a common technique in general in terms of statistics. It basically allows for using smaller sets of data and generating more data from a single data set. So anybody remember what I meant by bootstrapping? Anyone remember that phrase from prior lectures? Kind of? Well, the basic idea is you're going to create random samples, in this case, with replacement from your data set. And you're going to create multiple data sets through this random sampling. So this one data set can grow to more than one data set that way. Typically in bagging or bootstrap aggregation, the samples will be the same size as our data set, but you're going to randomly pick your elements from it within there. And then what you're going to do is from each of these now samples or new data sets, you're going to create your classifier. And then you run the classifiers on each sample. And then you're going to combine these. A common combination approach is simple majority voting amongst all of these random samples, or kind of random training sets that you create, these classifiers from your random training sets. So is the big picture fairly clear? Drew?
Yeah.
Question?
Not really.
Eric?
I get the basis of it.
The basis of it? Florida? Is there, I think their mic's off.
Do the hand up symbol if you have a question.
What does it mean of the same type of classifier? So like the same kind of data type?
Same kind of so you're going to create a classifier. So maybe you're going to use, I'll use a decision tree as an example. So you'll create a decision tree for each of your samples.
Okay.
Or I guess it could be, I mean, just looking at it, since you're going to be using majority voting, theoretically, I don't see why you couldn't use other types, as long as they output the same type of classification,
okay.
Whether it be binary. You know, it's hard to combine. You know, this is saying true, false, and this other one is saying 1, 2, 3.
Okay.
How do you make those match? I would have to think. I'd have to think about that a little bit. But immediately,
You make a match by asking a series of questions.
right? I mean, there's nothing. At least, given unless I run the classifiers on each testing sample, and then you're going to use majority voting. As long as they classify as the same type, I don't see why you couldn't use it in different types. So we get another subclass of bagging is called bagging with metacost. And this is used when each model, so each of your models can output probability estimates versus simple classification as face versus non-face, right? It could say, I think that there's a 0.8 probability that it's a face. So you're getting some additional information here. So, and so with these probability estimates, then you can use those estimates to obtain an expected cost of each prediction, where you would come up with some sort of cost function, and you would then classify your training instances to minimize your costs. And then from there, it learns a new classifier. So it's a different, so towards the end here, you're using these probabilities, and you're going to basically use them to combine at the end in a different manner. But again, the basic principle is the same. You're going to start with your training set, create your random samples. From those random samples, create each model, right? Except these models are going to now provide probability estimates instead of just a simple classification. Clear? Okay. Random forests. So this is a particular type of, I mean, one could think of it as a bootstrap aggregation applied to decision trees or tree learners in general. With one caveat there, that if you think of everyone recall decision trees, and what did we do for the first split? We split along the attribute that provided us with the most information gain, right, at the very first step. So what we need to do here is we need to use random subsets of our features, so that, because otherwise things are going to split primarily along the same paths each time. So by randomizing the subsets of the features, that's going to allow us to create different decision trees, if that makes sense. Yeah?
Wouldn't that just make a bunch of like useless trees then? And so you just, because it's all random, so you wouldn't want all of the decision trees, right?
Right, but you would still, so you're going to create random features, but still the stronger ones will still, you'll get more trees with the better splits than you will with the weaker splits.
Okay, gotcha.
Okay, so you're randomizing the attributes, but within each set of attributes, you know, so let's follow up on that, right? Is the smartboard's not working, so we'll start the whiteboard, right? So let's take a look at that, right? What were our attributes in the weather example? Let's just look at that. We had outlook. I want to, let's see. We had outlook. We had wind, if I could spell. We had temperature. We had humidity. And was there another one? Those are four main attributes.
Four attributes.
And then the class. Right? So there's our attributes, right? And say in one subset, right? I think when we did the decision tree on the weather data, Outlook came out the strongest. Was that right?
I think so, yeah.
So if I looked at Outlook, wind, and temperature, Outlook is still going to come out strongest
Okay.
in that group, right? If I look at Outlook, wind, and humidity, it's going to come out stronger. But maybe I come up with wind, temperature, and humidity. Now Outlook can't be the strongest one.
So that's going to be a weak
But,
one.
so you're going to have a different tree now. We're going to be splitting on one of those. Maybe you just look at wind and humidity, or Outlook and humidity. It's, again, every time Outlook's included, yeah, it's going to be included as the best split,
Okay.
right? So you're going to have more decision trees, or more of these trees with the first split being Outlook than with the other ones.
Okay.
But you will have other ones involved as well. So they'll be weighted, basically. Outlook will be the most weighted decision split for the first decision tree, but it's not going to be the only one. Does that make it a little clearer?
Yeah, that's much more clear.
Okay. So. Oh my God. So and here's the point, exactly as we just saw and I just described, Drew. By doing this, you're promoting tree diversity. So it's not always the same tree. And then you apply each tree and so on.
So does this help you see which attribute is strongest then? Or what exactly does this do for us?
In that example,
Yeah.
well, I mean, you're going to, okay, so let's back up. So now, what are we going to do from here, right? So, say we've got a tree. So let's go back to the whiteboard. So one tree, right? Let's erase this. Right? So let's say we've got one tree here, right? And I don't remember what how exactly the best ones went here. So I'm going to say, you know, maybe one tree was like this, and let's do another. This is kind of simple because we've only got 4 attributes, but humidity. Right, maybe we just had those 3.
Okay.
Maybe it looks something like that. Right? And now another tree over here starts off with what's the other? Wind. Right? And then I mean, we can have trees of different sizes. So there's an example, right? So now, what are we going to do? Maybe we even have a third one on that one as well. And then we're going to also split on temperature, right? So we have these, we have these 2 different decision trees. This is kind of the point here,
Okay.
right? And we're going to evaluate those decision trees on our data.
Okay.
Okay? On our, we'll train those using our training sets. then we'll test those trees, then we'll feed the testing data in, and those will make our classifications. So we'll get different classifications depending upon the different tree that we're looking at.
Okay.
So are you creating different trees for each probable outcome?
Well, some of these trees may appear more off, probably the better trees are going to, the better splits at the beginning are going to appear more often.
Mm-hmm.
And so you're going to get a preponderance of certain classifications. But it's you've got some diversity in there to allow for
every probability.
yeah, right.
Okay. Okay, so then,
So you're getting different classifications from your different trees, and now you're going to try to aggregate those together.
okay, and,
Using majority voting or what have you.
so each classification that we come up with for each tree is gonna have accuracy associated with it? Is that true?
Well,
That's if we're using the percentage.
right. I mean, on the training set, you're choosing the trees based on your subsets of your features
Right,
to maximize your performance
right,
on your training set,
okay,
right?
yes,
And because that's how the decision trees are formed in the first place. But now you're applying that tree to your testing data.
okay,
And that testing data, that testing sample, that tree will classify the test samples with particular outcomes.
So
okay,
you can have different outcomes like true or false or like
Right.
whatever.
So the tree on the left may take a sample and classify it as a face, and the tree on the right may classify it as a tank.
okay. So we end up with another, like a true, false, yes, no thing?
Right.
Like what the algorithm thinks it is and what it actually is? Right, what are those things called?
Right, there's going to be errors. There's going to be errors
Right.
when you actually apply it to your testing set. Right.
Okay. Okay,
I mean, no algorithm is perfect.
okay.
I can speak for myself.
And end up with.
Humans certainly aren't perfect.
So the confusion matrix.
Does that clarify how
I think so.
how that works?
Yeah, I'm just trying to relate everything.
Okay. So back. Is this where we? I want to make sure.
There. That's where we were starting.
So we just finished that.
Yeah.
Good. So the next big class of ensemble methods model combination is called boosting. In essence, this seeks models that kind of complement with an E, okay, meaning filling in the weaknesses of other models. So they complement each other. So where one might be strong, the other will be weak. Again, it combines models of the same type. And the idea is that when you create new models, we want to construct them to better handle those instances that were incorrectly handled by your earlier models. So in other words, it's a way of focusing on your samples, examples that are harder to classify. And the way that this is usually done is through weighted averaging, usually through an adaptive mechanism.
Like what?
So in terms of boosting, you mean the adaptive averaging?
Mm-hmm.
So let's see an example here. Basically, by weighting your your models that perform better on certain instances. You're going to weight those more for those instances than you will the weaker models. And as you start constructing your new models to fill in your weaknesses, you're going to adjust those weights, adapt those weights, so they're not fixed.
So you use like a slider bar or something.
Right.
Um,
So as you go through, yeah.
Could we use the temperature or the weather model as an example with this also? The two decision trees, I guess? I'm just asking.
no.
I'm trying to think of like the outlook, how the outlook had the greatest influence.
Right. So the outlook had its greatest influence, and I guess I would have to come up with an example.
Okay.
I don't have an easily, readily available one.
That's fine.
On the decision trees, that was pretty straightforward. I would have to think through one here.
Okay.
I can.
Well, it was just an example, right? Because a decision tree is a specific model.
Right. It's
So
a
we
right.
compare that one decision tree against another one, possibly, and weight which one, or is it already weighted with the decision trees?
Well, you've already taken care of some weighting there through your random sampling of your features, right?
Yeah.
Let me get back to you on that one. I mean, those are really good questions and something I didn't obviously think through when building.
I don't
Those
even
slides.
know if
Something
my
simple
questions are
like rain
relevant, but
and
that's where my
snow.
mind's at right now. So.
And rain could be one model and snow could be another one, because there's models of the same type and yet they complement each other because they're like opposite type of the same.
Yeah, let me just let me hold off. I don't want to mess things up. So.
Okay.
Let me, a big class of algorithms. I mean, I've used some boosting. I've not really, part of it is I've not gone into the depth of it. Well, for example, this is an area that I'm coming up with where I've done quite a bit more. So that's partially why I want to come back to that. Sure. Stack generalization. Here's one, James. I have a little bit of when it was introduced. 1992 by David Walpert, who at the time was at just down the road here, south, a couple hours in Los Alamos National Labs. Other algorithms trained from training set. I don't know what I meant by that. One of the things about stack generalization is it's really useful when you've got different types of models. They're not all the same type. They're not all decision trees. They could be just many different types of algorithms. And what we're going to be looking at is the stacking refers to using our initial classification from each of our what are called level 0 algorithms to build what we call level 1 algorithms. And I'll go through some of the details here. So we start off with, again, a training set. And we're going to do some J-fold cross-validation of the training set. So anybody remember what that meant? So maybe it's 10-fold. So we'll split the training set into 10 different pieces, right? And how that worked would have been, I'm going to use 9 of those pieces as my training set, and I'm going to hold out 1 piece as my testing set. That's going to give me 10 different training sets and testing sets, because I can hold out a different piece each time. And the J could be, you could have 3-fold cross-validation, so on. And now we're going to train and test each of the level 0 algorithms using the split training data. And that's what we're going to use to build our level 0 models. So in that example of 10-fold cross-validation, we'll hold out, we'll use 9/10 of the data for training and 1/10 of the data for testing, and that will create one of our models. And then we'll use a different piece, different 10th of the data held out, different 9/10, and that we'll use to create another model. And so this will generate a number of models. And we'll test each model on each split, and all of this is then used to create the data for level 1. So we're going to test each model on each split, and we use that to create our, basically by doing that, we've now created a large set of data that we can now use on our next level. So here's a diagram, right? So here we've got 3 different classifiers that we created at the level 0 point. And we feed the training data in, we get an output data, and then that gives those output values. We now are building a level 1 classifier using these output values as training and testing data for our new level 1.
So basically, you're taking your data, you're adding classifiers to it, and getting a different output, then putting all that data into another classifier and getting another output value.
Right.
Okay. So you're refining your data, basically.
You're right, exactly. Okay. And yeah.
So if you had another level 1 classifier and then a level 2 classifier, would all the level 0s go into both of the level 1s? Or would you have some go into one level 1 and some go into the other, or something?
Well, if you had them all, if you had the same ones going in from level 0 to level 1, and if you repeated those down here, you'd end up with exactly the same classifier at the level 1.
Well, I was saying, like, you've got more than one level 1 classifier and going into like a level 2 classifier.
Does that kind of depend on the data?
No, I mean, yeah, I mean, so you're asking, hold it, wait for it. You can create multiple levels of stacking. I call it stacked stacking. In fact, I've done this in the past. I can't remember the results, how successful they were, but I do remember experimenting with stacking the stacked classifiers. But some characteristics of stack generalization, it can be used both in a supervised manner or unsupervised manner. And I don't know if anybody remembers, a number of years ago, Netflix had a competition for the recommender system for, you know, if people are familiar with Netflix,
Yeah.
and you rate your the films that you watch.
Yeah.
And what does Netflix do with that? Well, they try to use that, your ratings, to recommend films, other films that you might be interested in. So they had a number of years ago, they had a competition to improve their system, recommendation system. And in that competition, I think the top two performers were both used some sort of stacked generalization to achieve that.
So what would they do? They would take their level 0 sets as what, individual person's ratings or something?
In that example, they might have, I'm not sure because I don't know all the details of how the winners actually, what level 0, right? So, so here, your level 0 classifiers can be all kinds of classifiers. They can be the same kind. You can mix and match. You can have a rule-based classifier and a Bayesian classifier, a decision tree.
Okay, so what those...
And I don't know what they actually used or whether they used Netflix original recommender system and just built a stack generalization from that.
So the different types of classifiers, would those be our level 0?
Those would be your level 0.
Level 1?
Right.
And then each
And then what kind of a level 1 are you creating?
I don't know.
So you can create a different types of level 1.
Okay, so then the level 1s that you get from each 0 classification you put into a level 2?
Generally, I mean, I experimented with that, but I mean, generally what I see in the literature, most people stop at level 1.
Okay.
Again, I did experiment. I can't remember what the results were on our particular problem with that I was working on.
So, you said the classifiers can be different?
They can be different.
How would that end up? Why would, okay.
As long as I mean...
Yeah, I guess...
because all you're interested in is what the outputs are giving us. And we're feeding those then into a new classifier.
So you're just...
Instead of like a majority voting than some of the prior ones, we're actually using those outputs to generate new data. Those outputs are our new data set.
And then you're putting it
And that we're now building a new classifier with.
I don't know if you throw another pool base in there. If this algorithm says true and this one says true, then we've got a probability that it really is that.
Right.
Okay.
Is that good? I mean, stop me if it's not. I can go back. Oh, I repeated here. And again, can create multiple layers, stacking. We already talked about that. It tends to, Tang and Witten in 1999 showed that stack generalization in general works best if you have used class probabilities versus binary classification.
Makes sense.
And, okay, the last big class, I'm glad I took out one of the ones I was going to go over, is called Bayesian model combination. And so really Bayesian model combination took some prior ideas and made it workable and better than the two prior ideas. So it's built upon this concept called the Bayes model averaging and Bayes optimal classifier. So let's start off by looking at what is a Bayes optimal classifier. And there's a fancy looking formula there. But it's an ensemble using Bayes rule, which you kind of see down below there. of all your hypotheses in your hypothesis space. And the key takeaway is, on average, it's an ideal ensemble. But, you know there's always a but, right? I maybe didn't put that in there, but it's impractical. You almost can't get there, right? And part of the problem, and I think I might have just gotten these in the wrong order. No? Okay, maybe I... One of the problems is huge number of hypotheses in hypothesis space. Other difficulties are coming up with your probabilities.
Yeah, okay.
Okay, so estimating your probabilities. So yes, in theory, it's nice. In practice, it's not practical. So to overcome this, people came up with what's called Bayes model averaging. I'm kind of going through a very simple example here. And the idea here is, okay, we can't get that Bayes optimal classifier in practice. It's too computationally intensive, it's too hard. How do we figure out these probabilities? So rather than use all the hypotheses, all the possible guesses that we have, we're going to just take samples. And the most common is probably what's called Monte Carlo sampling, which is just random number sampling, your most basic type of random sampling.
So, that replaces the stuff that you take out and gives you a new sample every time?
You mean with replacement?
Yeah.
Or, yeah, you could do with replacement. And there's other kinds of sampling that one can do there, but I'm not going to concentrate on that. Problems, it still tends to promote overfitting because it tends to, I think that was one of the problems with the optimal classifier. It tends to lead to one particular one being chosen. And here's the important takeaway always is empirically it doesn't do as well in practice as simpler methods like bootstrap aggregation and bagging. It's nice in theory, and this is a common takeaway in data mining. Just because you have the neat, complicated theory to support it doesn't mean it's going to work better than these very simple
CPU efficient.
More like the
Computational efficient.
The simplest sometimes, yeah, Occam's razors are to the rescue, right? So finally, Bayes model combination is a correction to Bayes model averaging. It uses model weights to create your samples, and it overcomes the drawback of Bayes model averaging, which gives extra weight to single models that it shouldn't. And now it actually does give better performance than bagging or Bayes model averaging. So modifications help there. And I kind of went through that really quickly at the end. You mean the outputs that are being used as now your new training data?
Yeah.
So your question how that works?
Yes. You put out to the confuse because it's the diagram of the two layers. If you go back a few slides to the stack generalization, go back.
Here?
Yeah. So I'm not sure. I try to guess because your training data into maybe 3 different classifiers, maybe the same classifier, but the output value, I'm not sure what that output value means. Is that a additional training instance like semi-supervised classification, or what's the value?
So you're getting all these values, right?
Yeah, and just the output value, what does this look like?
Well, it's going to depend on what classifiers you use there. So, I mean, it could be that for each instance, so you're getting a value from each classifier of, say, let's say it's a facial recognition. It is a face or it's not, a binary classifier, right?
You're really using the classifier, are you?
Well, I mean, so each output value could be a classification. It could be yes, no. So those could be your output values. Now you still have your, you know what the actual classes are, right?
I have a little hard time to follow yeah, just say it again, please.
Okay, so you still have, right, you've set aside, you know for your training sets, you know what the actual classification should be, right?
Yeah, of course, yeah, you know it is, that's why the training set, yeah.
Right, so now, your output your output value is going to be the value from each classifier, and some of those will be right and some of those will be wrong.
Okay, yeah, okay.
Okay, because you're always going to compare it to the actual value. So, but now you're going to take those output values, and you still have that actual value, and those are now going to be a training and testing set for your level 1 classifier. It's not working on your original training data now, it's working on the outputs of the classifiers as your training data for your new level 1 classifier.
Okay, so refining of the classified process, okay.
So you're building upon the outputs, not on the original data anymore. Your outputs become your next level of data for your your training data for your next classifier.
Oh, okay. It's like a collaborating. It's just like tuning up.
Right, and that's why you can go from one level to the next, and you can keep this process going on.
Okay. I think I got it.
You think you have it? I can refer you to some papers on that. I think Ting and Witten had a good description of it. But basically, you use the training data to train your original classifiers, and they give an output. And those outputs are now your training data for your next classifier. Hello?
Yeah, I can hear you now, and my voice now it's better. I just okay. The reason I asked that, I'm confused, is because when you use the semi-supervised training, you use the same kind of diagram. You can use the small size of the training data and use the classified
right.
data. You get more data because you classify, you trust it. And they use that data to future to training more for your model. That's another
Supervised.
Basically, more.
Right, I mean, this diagrams could be used in a lot of different places, right? Even if you think about just simple averaging of your outputs. You could think of this classifier as just being the average of all of your outputs. But stack generalization is saying, look, we can use any classifier here as your level 1.
So in this case, we're talking about the same type of classifier, basically.
Well, no, you can use many different kinds.
You can, yeah. In the first, you can use differently. You can use differently, yes.
You can use different ones at your level 0. You can use any classifier you want as what you're going to apply for your level 1 classifier.
Yes, yes.